In this lecture, we are going to discuss about the solution of an important but easy problem of bounded set. Or we say that it is a theorem on bounded set. And this theorem says that if A is bounded subset of reals, this is capital R, containing at least 2 points, right? And if B, the set B, is the set of all upper bounds of A, then show that B is non-empty and also this is bounded below. And we have to prove also that infimum of B, this is equal to supremum of A. Okay. Here we first say, or we first use the definition of a bounded subset of R. Here we first write, since A, this is a subset of R, is bounded. So from the definition of bounded set, so there exists U V belongs to R such that U less equal to A less equal to V for all A belongs to A. This is the definition of bounded set, right? And we know from the properties of bounded set, since A is bounded, so supremum of A exists. Okay, let supremum of A, this is equal to capital A, right? This is the property of bounded set. That is, the bounded set has supremum, also have infimum. Here we have to require only supremum, so we let supremum of A, this is equal to capital M. So by the definition of supremum, we can write two properties. The first property is, for all A belongs to capital A less equal to capital A. This is the upper bound property. This is the first property of supremum. And the second property is, there exists at least one A dash belongs to A such that A dash, this is given by greater equal to M minus epsilon for any epsilon greater than 0. However, it can be small. Okay, because supremum, if this is A and supremum is at the upper boundary of the set. Okay, this is the set A and this is the position of supremum, this is capital M. So if we subtract any positive number from M, then we get a number here M minus epsilon. Okay, and in this case we get here A dash, this is belongs to A, obviously, right? This is the second property of supremum. Now we have to show that B is non-empty. Here we first define the set B. The set B is the set of all upper bounds of A. And from the definition of supremum, and supremum is also known as least upper bound, right? Least upper bound, LUB. That is the list of the all upper bounds. And we know that since M is the least upper bound of A, so any number greater than M is also an upper bound of A. Okay, so we write here any real number greater than M is an upper bound of capital E. Okay, so we get infinite number of upper bound of capital A because any real number set have infinite number of point greater than n, right? So the definition of B can be written as, now B, this is equal to small b such that small b belongs to obviously R and small b, this is greater than n or may be equal to n, because B contain the points which are the upper bound of the set A, and since n is the least upper bound, so n is also a member of B. Also we say that any number B which is greater than n is also a member of B, right? Now we have to see that, or we have to prove that the set B, this B is non-empty and this B is bounded below. Then we have to prove that infimum of B, this is equal to supremum of A. We prove one by one all three conditions, and we already says that since there exists infinite element of R, okay, of set of real number which are greater or equal to m. We know that greater or equal to m, there are infinite number of element of R. So B not equal to 5, right? So this is the proof of the first case. This is B is non-empty, right? And the second case is, since for all B belongs to B, we write B greater or equal to M, and this condition says that B is bounded below and M is the lower bound of the set. So we write here B is bounded below by capital M. Okay, and this is the second condition we proved already. Now we have to see that infimum of B, this is equal to supremum of A. We already here let supremum of A, this is equal to capital M, right? And now we have to prove that capital M is also the infimum of B. And two properties of infimum are, first property is already here satisfied from the definition of B. So we write the first property, for all B belongs to B, there exists M belongs to R such that M less equal to B. Okay, this is the first property of infimum. Now before writing the second property of infimum, we let delta any positive number however small. Okay, and since delta is any positive number however small, now M plus delta, this is obviously greater than M, right? Since delta greater than 0, and since M plus delta is greater than M, so M plus delta is an upper bound of capital A, right? Upper bound of capital A. And since M plus delta is upper bound of capital A, so it must be belongs to the set B. Okay, so this implies M plus delta, this is belongs to the set B, right? And obviously here we already write M plus delta greater than M. Okay, and since this and this are two real numbers, so there must exist a real number in between these two number, and simply we write m plus delta. This is greater than m plus delta by 2, and this is also greater than m. Okay, and we may write this is delta by 2 or delta by 3 or delta by 5, etc. Whatever you want, right? And this number is also an upper bound of capital A. Okay, so this number also belongs to capital B, and we name this number as B dash. Okay, and so we write the second property of infimum. This is there exists B dash, and which is given by m plus delta by 2, right? M plus delta by 2, such that, we write first this is belongs to B dash, this is belongs to B. We prove here B dash belongs to B, such that B dash is less than m plus delta. Okay, for any delta greater than 0. We already proved here m b dash less than m plus delta. Okay, and obviously this is the second property of the definition of infimum. Okay, this is the second property of infimum. So we say that capital M, this is equal to infimum of B, and we already let here capital M is the supremum of A, and from this and this we can write this proof: infimum of B, this is equal to supremum of A. Very interesting and very easy proof or very easy theorem of bounded set. Okay, thank you for watching.